Hi, how you guys doing? Alright, let's get started, shall we? Today we are going to talk about a new concept, okay, called chemical equilibrium. You guys ready? In the past, we have treated chemical reactions as they go in one direction and they go to completion, okay? One direction and completion. Considering the first reaction right here, the reactant nitrogen dioxide. This guy is a brown gas, okay? And it's unstable at room temperature, unstable. If you dimerize to making product, the colorless product, dinitrogen tetraoxide, no color. Now I'm asking you, since this guy unstable, what would happen? Let's say we have a container filled up with this gas, nitrogen dioxide. Leave it at room temperature for a period of time. What's going to happen? So we think that unstable, okay, the color will get lighter, lighter, and become colorless, become dinitrogen tetraoxide, right? And we say, oh, it go in one direction and go to completion. You don't see any color, okay? In reality, we are chemist instructor kind of lie to you. Sorry about that. But most chemical reactions don't behave as one way and complete reaction. Okay, they don't behave as one way and complete reaction. What really happens? Take a look. Brown color get lighter, 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 lighter. It's not become colorless. You can see that. You see some color left, right? So they don't go to completion normally. Okay. Surprisingly, let's say we start backward. Dinitrogen tetraoxide, colorless. Okay, start with this guy. Leave it at room temperature for a period of time. What happened? Take a look. The color gets back up. Okay, the colors get back up. Looks like chemical reaction don't, first of all, they don't go to completion. And they can go backward. You see that? This is from product, right? They can go backward. In reality, okay? In reality, most chemical reaction exist in, new word for you, equilibrium. Okay, turns out they all exist in equilibrium. What does that mean? I'm going to explain to you, but before that, I'll give you two terms. Okay, I'm going to be using. First of all, forward rate. The rate from reactant become product. Okay, and backward rate, or in the text they say reverse rate. It's the same thing. Okay, from product back to reactant. All right. Here is the meaning of equilibrium. Okay, most reactions behave this way. At the beginning, we have high concentration of this guy, nitrogen dioxide. Okay, we have high concentration of reactant. Since we have high concentration, how does it going to affect the forward rate? You tell me. High concentration of that, fast, right? Go real fast. Okay, so as nitrogen dioxide react to each other, okay, to make product, concentration drops. How does that going to affect the rate? Lower concentration. The rate will be slower. Okay, it's slower over time, slower. All right. At the same time, the product, okay, the product gets built up. Okay, it gets built up. As we have more concentration of product, how does that affect the backward rate? Tell me. It will go back faster, okay? Have more of that available to break up to the reactant, so it gets faster. What happened to increased concentration right here? Still increase, but slower, okay? Because it goes backward faster, okay? So, eventually, these two processes, go forward and go backward, will reach to the point that both rates are equal. They happen at the same rate. And we don't see any change in concentration right here. Okay, we don't see any change in concentration. And we call this point equilibrium. Okay, kind of balance between forward and backward rate. All right. Note that I didn't say that the reaction stopped. Right? Didn't say that. Didn't say that. The reaction never stopped, like ever. Like seriously, they never stop. Forward rate, backward rate, still occurring, continues to occur. But once they reach the point that forward and backward rate happen at the same rate, that's why we don't see change in concentration right here. Okay? And we end up with mixture of product and reactant. Can you follow me? We end up with a mixture of product and reactant. All right, so this is the concept of equilibrium, okay? Now, pay attention to this word, mixture, okay? We end up with a mixture. Since most chemical reactions exist in equilibrium, we're gonna get mixture of product and reactant anyway. This is kind of a sad news for chemists, okay, who make their living by doing reaction to make product. They want to make a lot of product, but they said, oh, you're gonna get mixture. It's sad news, okay? However, chemists are smart, okay? Here's what they think. They think, huh, I'm getting mixture. What do you really mean by mixture? It's a mixture of 1% reactant and 99% product. That's a great mixture. I like that, right? This is a good mixture. They'll keep them happy. Or 99% reactant and 1% product. That's a bad mixture for them. If this keeps happening, chemists will get fired. Okay, they can't get anything done, right? Or 50-50, not desirable for them. So, when chemists do reaction, they are interested in position of equilibrium. Position. Okay, they want to know that if the reaction that they are doing favor product, reactant, or neither. Okay, they want to know this. So they come up with a way, okay, to determine the position of equilibrium. Here's what they do. Take a look. They take concentration of product over reactant at equilibrium. Okay, these are concentration at equilibrium. Product over reactant. And these two concentrations are powered by coefficients. Okay, they're coefficients. And they call the value that comes out, this fraction, that Kc, equilibrium constant. Equilibrium constant. Okay, C stands for concentration. Okay, and they use this equilibrium constant to determine position of equilibrium. Take a look how. Keep it easy. I'm going to make it easy. Nothing complicated. Okay. I'm going to make y and x just 1. Okay. Make it easy. All right. Let's say if Kc equal to 1 times 10 to the second. What does that mean? It means that at equilibrium, these are concentration at equilibrium, right? At equilibrium, the concentration of product is 100. Let's say molar. Okay. Keep it easy. Let's say 100, and that of reactant is 1. What does that mean? This reaction favors product, okay? And this reaction is, you have heard this word before, spontaneous. Keep the chemist happy. All right, we love this word most of the time. On the other hand, if the equilibrium constant equal to 1 times 10 to the negative 2, which is 0.01, okay, 0.01. It means that at equilibrium, concentration of product is 1 and that of reactant is 100. Now you can see that equilibrium favor reactant, okay? And we call this type of reaction non-spontaneous. Okay, sad news for chemists, okay? So I give you two numbers, 100 and 0.01, because as a cutoffs, okay? Any reaction that have equilibrium constant 100 or above are spontaneous. Those reactions who have equilibrium constant 0.01 or below are non-spontaneous. The one in between give us a mixture. Okay. All right. Let's stop it right here. Okay. So summary. We have learned about concept of equilibrium. Most chemical reactions exist in equilibrium. They never stop, like ever. Okay. But forward rate and backward rate can happen at the same rate. But once they reach a point which we call equilibrium point, they happen at the same rate, and we get mixture. Okay. And chemists who are interested in making product, so they want to know if the equilibrium favor product or reactant, so they come up with the equilibrium constant. Okay, so determine spontaneous or non-spontaneous. I give you cut off 100 or above or 0.01 or below. All right, let's stop it right here. Okay, next time we're gonna talk about how smart chemists are. Okay, chemists are interested in making product. They want to make a lot of product. So they have tricks, okay? They have tricks that can manipulate equilibrium, force equilibrium to give them product. Okay, we're gonna talk about that when we discuss about Le Chatelier principle. Make sure you go review all this, and I'll see you next time.